On the first day of this unit, we looked at a lot of material surrounding sampling distributions of means. We looked at sums of samples and then converted that distribution to means by dividing by the sample size. This was done to derive the formula for the standard deviation of means and to realize that the formula makes sense mathematically. Or, hey, yeah, I just know it works so I use it, and that's fine as well. The second reason is to tell you this. You can always convert a problem like this, asking for the probability that the sum of 10 randomly selected haircuts exceeds 240 minutes, to an equivalent problem like this. Find the probability that the mean of 10 times exceeds 24 minutes. All you have to do is divide the sum of 240 by 10, and now we're dealing with means instead of the sum. By changing it to focus on the sample means, then we can always use sampling distributions of means and avoid the joint distribution of sums. And with inferential statistics in the next unit, it is the sampling distributions of means that we focus on. I'll provide more practice, but first let's look at two problems to gain greater insight. The first one is on this video. The second will involve us collecting data from the roll of 10-sided dice. A kitchen manager at a restaurant must keep careful track of all food costs. The restaurant purchases high-quality cuts of beef tenderloin. They vary in size and are charged by weight in ounces. Suppose the weights are normally distributed with a mean of 13.4 ounces and a standard deviation of 0.6 ounces. If we randomly select 20 cuts of tenderloin, find the probability that the mean weight is under 13.5 ounces. Here's the distribution of cuts one at a time. Let's determine the sampling distribution of mean weights of cuts from samples of size 20 and show it below the original population. And here is the understanding you really must grasp. One random sample of 20 cuts of beef may have these weights. We add those up and divide by 20, and perhaps that particular sample has a mean of 13.6 ounces. It's located here on the sampling distribution of means. Here's another random sample of 20. The mean of this sample is 13.35 ounces. See it in the sampling distribution of means. So every mean in the second distribution comes from a sample of 20 scores from the original population. Using the empirical rule, would it be unusual to select only one cut of beef and it weigh over 14 ounces? The answer is no, because this weight is at a z-score of 1. It's one standard deviation above the mean. Approximately 16% of cuts are above 14 ounces. But would a mean exceeding 14 ounces be realistic if a sample of 20 cuts was taken? Look at the original distribution one cut at a time. For us to get a mean of 14, we would need 20 randomly selected weights that are centered way up at 14 ounces. We'd have to have many weights be unusually high to accomplish this. That's not at all realistic. Now verify this understanding by looking at the sampling distribution of means. So getting one particular sample mean above 14 ounces is not going to happen. It's more than 4 standard deviations above the population mean. Now this should make sense that there is much less variance among sample means of size 20 than there is among individual cuts of meat. This is why the standard deviation for the means is the original standard deviation divided by the square root of the sample size. And the bigger the sample size, the smaller that standard deviation of means becomes, which makes sense because a larger sample leads to a more accurate result.